Now, I am very delighted to introduce our speaker today, Juan Felipe Carrasquilla. Juan's research interests lie at the intersection of computational condensed matter physics, quantum computing, and machine learning. He obtained his PhD in physics from CISA, the International School for Advanced Studies in Italy. Subsequently, he held positions as a postdoctoral fellow at Georgetown University, as a postdoctoral fellow at the Perimeter Institute here in Ontario, as a research scientist at D-Wave Systems, Inc., and as a research scientist at the Vector Institute here in Toronto. Since 2024, he has also been an associate professor of computational physics at ETH in Zurich. So today, Juan is going to be giving us a talk titled Language Models for the Simulation of Quantum Many-Body Physics. Please join me in giving a warm welcome to Juan, and without further ado, over to you.
All right. Thank you for the introduction. A pleasure to be here. And yeah, let me tell you about how we think about using language models for simulating quantum systems and quantum states. And yeah, excited to be here. So I guess the whole thing is, this line of research is shaped or is like within the context of this exciting moment in research, generally speaking, like technologically in the world, that in which researchers from many areas of physics, including particle physics, high energy physics, condensed matter, quantum information, AMO physics, and so on, are exploring ideas related to machine learning and its implication in these fields. And I refer to those of you that are interested to this review paper, where the authors explore all sorts of different applications in all sorts of areas of physics, as a kind of like a taste for how this research started a few years ago and how it looks like today, somehow, or how it was shaped to be what it is these days. And this is all inspired mostly by this deep learning revolution that started in computer vision, in natural language processing, and so on, right? Like on all these beautiful research areas, including physics and chemistry and so on, which is driven by the, if you want, the availability of massive data sets, specialized hardware, like GPUs and so on, but mostly, and also algorithmic developments that have created or given rise to this beautiful generation of models displaying and presented accuracy in so many different ways, and so many different arrays of technologically and scientifically relevant tasks. And here I have some example of diffusion models, which can create this beautiful artistic pictures based on prompts and so on, which have lead to impressive results in many different areas and fields of research, including chemistry and so on, but also art. Okay, so in quantum science, there's a lot of basically every single aspect of quantum science research is these days touched at least by machine learning ideas and its research culture, in particular in simulation of strongly correlated systems, like in chemistry, in density functional theory and quantum Monte Carlo simulations, for machine learning phases of matter, and simulations based on experimental data. There's discovery of new physical phenomena and laws from data, neural network representations of quantum states or renormalization group, and all sorts of applications in quantum information, quantum control, and quantum error correction, and much more. And for that, like I wrote a review paper already in 2020, so that's a little bit dated at this point, but it gives you a sense for how this idea, or these ideas from machine learning, are kind of like expanding within these fields of research, right? Like, so quantum matter research or quantum information and so on. So it's very exciting, and there's a lot. And this is shaped, in my opinion, in part by many commonalities among the problems that machine learning and physics disciplines address. And I'm going to talk about these commonalities and see if they're just a coincidence or if this is actually a useful thing to note and to exploit. Okay, and the first one is this high dimensionality, right? That's a very like it's something that we hear all the time in machine learning, this curse of dimensionality, and so on. And in quantum many-body physics, that's also true. So there's kind of like happening in quantum physics that arises because a generic specification of a quantum state requires resources that are exponentially in number of degrees of freedom. Okay, so we usually study quantum systems by constructing these gigantic vectors with, if you're talking about spins, like spins are objects that can be, say, up or down or 1 or 0. And then if you compose many of them, then you end up with a vector with 2 to the n components, where n is the number of degrees of freedom in this system. Like, for instance, if you have 3 spins, they can be in the 0, 0 state, 1, 0, 0, 0, 1, 0, 0, 0, 1, and so on and so forth, right? And the idea is that as you compose the system with more and more degrees of freedom, then the number of possibilities grows combinatorially, exponentially with this n, the number of degrees of freedom, and that's what we have to keep track on a computer if you want to simulate a quantum system exactly. Okay, so for instance, for 45 spins, which is a very small number for at least compared to the problems that we're interested in, that gives you already 10 to the 13 dimensional vector, which starts like becoming a severe limitation when it comes to studying the systems. Okay, so that's the high dimensionality of quantum mechanics. But then if you think about language is also very high dimensional. So you can think of probability distribution over language. It's also a very high dimensional vector. And you can think of the size of the probability distribution as being composed of a vocabulary size, which is basically the number of words or the number of tokens in a language, to the power of the maximum length of a sentence. Okay, so it's kind of like how many paragraphs can you write, right? How many different paragraphs can you write given a maximum sentence, the maximum length of a sentence and a particular vocabulary, right? Like so. And you can think of this as like if you want to read a newspaper article, you need about 8,000 words to understand your average journal article, and then 100 words. Let's say if you're talking about a word vocabulary, and that gives you already 2 to the 10 to the power of 390, which is way bigger than, for instance, the number of atoms in the universe and so on. And so that's crazy, and that's impressive, but also at the same time is exactly what modern language models deal with these days, right? Like, so if you so this is an example I took from this paper, Attention is All You Need, which introduced the transformer architecture. So I guess the message that I'm trying to convey here is that these large language models live or encode distributions that live on extremely high dimensional spaces. And even though those are incredibly high, like the language models or the distributions are powerful and allow us to make progress. Okay, so that's the first commonality. So it's this very high dimensional objects that we both fields study, right? Like quantum states and NLP models. But nevertheless, so even though they're so big, they're actually quite structured, right? Like, so many quantum states realized in nature live in a lower dimensional subspace out of this gigantic, we call it Hilbert space. So basically, if you draw a random state in this high dimensional space, then we get what we call a typical state. But the vast majority of states that are realized in nature, that we believe are realized in nature, that we call physical states, are not a typical state. They have a lot of structure, right? Like so. Because they describe interacting systems, and the interacting systems are local somehow, like particles when they're close to each other interact very strongly, but when they're far apart, they do not interact at all, okay? And this puts some constraints on the physical systems that get realized in nature, okay? And the same is true for language, right? Like, so there's distributions that are realized on language, in particular, say, for instance, the language that we write on the internet and so on, it comes with a lot of structure, right? Like, so they're not random paragraphs, okay? As they happen, they convey a meaning, and this meaning is easy to understand for us humans and so on. And that endows those distributions with a specific structure that we can exploit. And it's the only reason why we can do, in fact, machine learning on such large scales with success, okay? So what happens is that both in machine learning and in quantum physics, we exploit the structures, right? Like to make progress in our understanding of the problem, or to generate new technology in the context of machine learning. And in our context, like this, what happens is that the amount of information in these states that we see in nature is usually smaller than this largest capacity, right? Like, so we have this structure and we exploit it. And like, for instance, we use, instead of exploring this state space exhaustively, what we do is we sample it stochastically, basically mean that we visit the most important regions of configuration space, and then through that idea of exploring it stochastically, we can make progress, and we've made progress through the years by using tools like Quantum Monte Carlo. Or if the states that we're interested in studying have little entanglement or little correlations, it turns out that we can use a technique called tensor networks that allow us to factorize these quantum states and parameterize them with much fewer parameters than this exponential complexity I was talking about. And using these techniques have led to profound implications in our understanding of quantum systems, and so they've been very important in the last 40 years or so. And in machine learning, that's exactly what happens. So machine learning techniques exploit the structure present in natural data sets like images and natural language. Like, for instance, in convolutional neural networks, people exploit the fact that there's numbers can be seen anywhere in the image, but then they always mean the same, right? Like, meaning that there's some sort of shift invariance to the problems that we study, and so people naturally exploited those structures to make progress in, for instance, in computer vision and so on. And then there's a commonality, right? Like that physical systems include correlation functions and symmetries that are very similar to those that are used in machine learning as well. Like, for instance, the example of translation or shift invariance. Also, rotations are present in data, such as reflections and many more. Okay, like, for instance, if you take a zero and then you rotate it, that's that perfect zero, let's say. A circle represents a zero, like that it should be always recognized as a zero regardless of how you rotate it, right? Like, so, and that's called rotational invariance, and we also exploit that when we do, say, computational quantum physics, right? And there's many more of the symmetries that are common to natural data sets and to computational quantum physics problems, and so the idea, or the question is, can we exploit the insight that both quantum and machine learning problems have some sort of common shared structure, right? Like, that's kind of like the premise, and the thing that we've been exploring for the last 8 years or so, and even beyond that. So are these commonalities even relevant for computational physics beyond the fact that they're just resemble each other? And yeah, that's what I'm going to be trying to convince you, right? Like, through a series of examples. And when we started doing this, we kind of like came from the natural language processing context. It can be broader, right? Like you can think of almost any machine learning problem and then transform it into a quantum problem or reformulate it as a quantum, or in terms of like basically any, right? Like so computer vision, we've done it. We've like taken inspiration from all these fields, but many of the problems that we looked at came from thinking about natural language processing, which is this branch of computer science and linguistics concerned with giving computers the ability to process text and words in a similar way humans do it. And it's useful, as you all know, like in machine translation, speech recognition, and a lot more. And the example, of course, is ChatGPT, which has like he's having a very deep technological and educational implications and so on. But more like precisely so, like these models like are based on neural networks, right? Like, and they're powerful. These models are powerful universal function approximators that can in principle represent any function if you give them enough parameters. And in particular in NLP, they model things like this, right? Like so, conditional probability of given an input text that you sample or that you have a probability on some output text, which can be used for translation and, for instance, from Spanish to English and so on. And then, so that's kind of like where we start, right? Like this conditional distributions or this like high dimensional probability distributions that I was discussing earlier. And these language models, or at least the earlier versions, right, like the recurrent neural networks and the first transformer and so on, they looked a little bit like this. So there's an encoder in which you send the text, right? Like, so write a poem about quantum states, for instance, and they produce some sort of high dimensional representation vector, basically with D components, which encodes this input text, right? Like, and then there's a decoder that if you sample would produce sort of like a output, right? Like, so that's kind of like the prompt in the in ChatGPT, for instance, and then what you see as an outcome is kind of like a sample from that probability distribution. It doesn't have to be a sample, but there's one possible decoding strategy is sampling this probability distribution, and then you would see some sort of poem about quantum states, right? Like, which in this case is what I have here in the pointer. Okay, and so that's kind of like how these models initially worked. And this is like an example of a recurrent neural network, which at the time, I think this is 2014, they were state of the art. Okay, so you would have an encoder that would read the sentences or the prompt and so on, and it would produce this high dimensional vector H0 in between that encodes this ABC text. Okay, and then you have a decoder that you can sample. For instance, it would produce X, Y, and Z outcome, and then some end of sentence word here or token here, and which can be a sample or it can be decoded any way you want. And that was kind of like state of the art at the time for sequence to sequence learning in neural networks already more than a decade ago. The original transformer looked exactly the same. It had an encoder that would be like this attention mechanism that would produce high dimensional vector H0, and then that would be passed to a decoder, which is this big, again, attention or deep multi-head attention layer, followed by some sort of like softmax, okay? And that basically, as you all know, revolutionized NLP and so on. But basically, what I wanted to emphasize is that it follows the same structure, and decoder, encoder, high dimensional vector, and then a decoder, okay? And what we did was we took inspiration from this, and we made it both from the RNN and from the transformer. We made it a central ingredient behind our work. And what we did was modify this architecture so that they represent both classical states and quantum states inspired by this NLP, okay, architectures. And we've done a lot of it. So we've done quantum state reconstruction. So that was one of the first ideas related to using these models for representing quantum state. We've simulated quantum circuits with transformers. We find recurrent network wave functions, which are extensions of these models to quantum states. We've used them for computationally hard problems, like in combinatorial optimization, and a lot more. So for neural error mitigation, for simulating open systems with transformers and so on, and a lot more. So we've really done a lot of work in this area. So the question is how to use these models to represent physical states, right? Like that's the main question. So generally speaking, we got rid of the encoder, which is similar to what happened with GPT. Eventually, they got rid of the encoder and then only have a decoder model. Okay. Okay, so we don't have a decoder. We take this vector H0, we set it to a bunch of zeros. And then the next thing that we do is, so instead of words, characters, or tokens, we replace that with the degrees of freedom of the system. So if you have, instead of tokens or words, A, B, C, or word A, word B, word C, we replace this with the degrees of freedom of the system. For instance, spin up or spin down, or outcome A, B, and C, and so on. So basically, replace the words and characters with the degrees of freedom of the system in some basis, some computational basis. And that gives you a probability distribution over the possible measurement outcomes, for instance, in a quantum state. Okay, but that's not enough to. So this is basically changing just what I said, changing words for degrees of freedom, spin up or spin down. But that's not enough to build the quantum state. So quantum mechanics represents states as complex amplitudes, right? So basically, it's not just a probability distribution. You need to add a complex phase to it. And so that was kind of like the modification that we did to to these models, is to supplement them with a phase that we can hopefully train also. Okay, so that they represent quantum states, and so that's how we build our wave functions, right? Like, so we get rid of the encoder, we keep the probability distribution, take the square root of it, and then add some phase. Okay, that's all we've done, and this phase can be done very much the same as like you do with a transformer. You have a softmax layer that gives you a probability distribution. We can have an extra layer at the top of the transformer or the RNN and give it instead of a probabilistic outcome, a phase factor that you can define a complex phase. And so that's what we do. Okay, and now we have a well-defined quantum state that's based on or inspired by this natural language processing idea. And these models are autoregressive, and so basically meaning that computing the probability of a sentence, for instance, is efficient. In this case of quantum state, it translates into computing the probability or the amplitude of the wave function, and that remains efficient. These models can be sampled exactly, efficiently in linear time in the number of degrees of freedom or words in a text. They can be defined in any spatial dimension without tractability issues. If you compare that with other approaches in quantum many-body physics, that's gives you an advantage. And the other thing that we find really appealing is that their expressive power can be systematically improved in a recurrent neural network is through the dimensionality of these hidden vectors that get passed around, or in the dimensionality of these hidden vectors in the transformer, and so on. So that's really exciting. We can encode mean field theories, we can impose symmetries and conservation laws, and so on. So we think these are very powerful architectures, and we can take inspiration from all the ideas already developed in machine learning. And we can also add more based on our intuition and knowledge of the physics of the system. Okay, and as an example, or as a few examples, I'm going to focus on computation of ground states of quantum many-body Hamiltonians. A Hamiltonian is kind of like the function that defines the energy of a system, but for quantum systems. Okay, there's kind of like a generalization of the idea of energy, but to a quantum mechanical system. And the idea is that we can that computing this energies is very complicated in quantum systems, and that these Hamiltonians, instead of being a function, they are matrices that are very large. They're very basically exponentially large, and so diagonalizing them, which is a process through which you would go traditionally, becomes very difficult because of this sheer size of the matrix. We cannot even store it in any computer, not even the largest computers like in the world, the largest supercomputers. So, but we can write them down. We can write them down analytically, anyways. So we can, yeah, that's the idea, that we would like to understand if we can compute these ground states or the low-lying eigenvectors of these gigantic matrices. Okay. And we do so without data. So, okay, that's the other thing. So, because these problems are completely intractable, we have to rely on other ideas, and there's no way of generating data out of them. Okay, so the idea is then that we use some sort of variational principle that doesn't require data, but that allows us nevertheless to try and approximate at least a few of the eigenvectors of this gigantic matrix. Okay, and that's exactly what we've done here, and this work by my former PhD student Mohamed Hibat Allah, who he recently joined actually University of Waterloo as a professor in applied math. So I'm very proud of him. So basically, he developed this framework to train recurrent neural network wave functions to approximate ground states or eigenstates of this Hamiltonians, that they're very like simple looking, but they hide a lot of complexity, right? Like, so you can write them down analytically in one line, okay, but if you were to write them on a computer, they would be exponentially large. So we cannot fit them. We cannot fit them in the memory of not even the largest supercomputing in the world. Nevertheless, we are able to exploit the structure of the problem to compute at least a few of the low-lying eigenstates of this gigantic Hamiltonian. And for instance, this is basically the computation of the ground state energy with respect to the exact solution. So this is for a problem for which we know the exact solution through analytical means. And what we see is that the error as we train these models becomes very, very small and compatible with state-of-the-art methods in computational quantum physics and beyond. And then we compared, say, for instance, correlation functions, such as spin-spin correlation functions as a function of the spatial separation between, say, 2 points in the system, and then they match really perfectly the state-of-the-art techniques like DMRG, density matrix renormalization group, and more. And this is computation of entanglement, which, if you want, measures how correlated or how strongly correlated this spins end up being due to the interactions in this Hamiltonians, and they all match really well. So we were really excited to see this seemingly unrelated architectures coming from natural language being capable of simulating quantum systems that are in principle, nevertheless, that are in principle completely unrelated to NLP. Then we went and defined them in 2 dimensions. So that's much more difficult to do with traditional techniques like DMRG or density matrix renormalization group. And we were able to find that these architectures are performed better than the best tensor networks or DMRG techniques. So we're able to get more and more accurate solutions to the problems at cheaper computational cost. So that was really exciting to see. Also in 2D. So the first examples were in 1 dimension. Now this is 2D, where we can still do some calculations, but they become much more difficult. And this is, again, another example in 2D where we're able to match the results with the state-of-the-art results, and basically telling us that these models, these recurrent neural networks, eventually become nearly, or they have a high of a quality that's as almost indistinguishable from exact methods, meaning that we're just really building a really strong tool that we can use to explore unknown physics, that I will, for instance, explain in a little bit, that we've been using to try and explore physics beyond what we can do with traditional techniques. This is another example in 2 dimensions. It's a more challenging example from Skylar Moss at the University of Waterloo, where she was able to simulate a much more challenging example in the literature. There's this Heisenberg model on the triangular lattice, which is just a little bit more challenging than to simulate, and she was able to get state-of-the-art results again with this same recurrent neural. And these are the results. So basically, to just flash quickly that these lines here, IPEPs and DMRG, were the state-of-the-art before what we've done. And lower energy means more accurate calculation. So we were able to get lower, so improving a bit on the state-of-the-art calculations on the calculation of the ground state of this quantum system. Okay, and so that was very exciting to see. This is from I think this was published only recently in Physical Review. And then, okay, so that concerns studying phases of matter that are, if you want, magnetically ordered. So phases of matter that can be basically understood by taking a look at how the spins behave, right? Like, so basically, if you take a look, the spins basically aligning this pattern. Okay, it's a pattern that we can understand. So every 1, 2, 3, every 4 sides, this pattern repeats, right? Like along this direction and that direction. Okay, so 1, 2, 3, 4, and so it's kind of like you would take a look at it spatially, and you would see a pattern, and we call this pattern magnetic order. Okay, and so we're able to reproduce this. But interestingly, there's a phases of matter that cannot be described by these patterns, right? Like, and they're called phases endowed with topological order. If you look at them, they look completely random, but they hide a lot of complexity. And we wanted to see if this recurrent neural networks could capture also phases of matter which have this disorder, but topological order. Okay, and they're interesting because they defy the Landau paradigm of classifying phases by symmetry, and they're distinguished by more subtle topological properties that are more difficult to capture with traditional techniques. And basically, the grandmother of these phases is the ground state of this Hamiltonian. It's called the toric code. It was introduced by Alexei Kitaev as a toy model for topological quantum computation, and it's very rich. It has this topological order that I was discussing, and yeah, so we wanted to understand if our neural networks could capture this richer or more exotic phases or family of phases of matter. Okay, and that's something that I had already explored before. So actually, my first paper on machine learning, actually in 2016 and 2017, we explore how to write down this ground state of the toric code already exactly using convolutional neural networks, and that was kind of like my first ever paper on using machine learning ideas for physical systems. It included this example. So we were able to write down ground states of this Hamiltonian using very shallow convolutional neural networks. And so we thought, okay, can we do the same with this models inspired by NLP? Okay, as an example. Let me just very briefly tell you, so that we detect this models or this phases of matter through a calculation that's very subtle. It's called topological entanglement entropy. I think it doesn't have to, like, we don't have to go through what the details of this quantity look like and so on, but let me just tell you that for the toric code, this topological entanglement takes, so we know what we're expecting in this, at least for this type of phases of matter, so it's log 2. And let me show you whether we recover it or not with the RNN, but the idea is that we do. So if we took a look at this toric code, and we were able to approximate the ground state with high precision, such that when we computed this topological entanglement entropy, we got exactly log 2, which is this related red line here. So we were excited. We didn't know, or we were, we wanted to verify that our wave functions would capture phases with like this topological order, and we were able to confirm that's the case here. And then, okay, the slide is a little bit messy, but I don't know what happened to it. But the idea is that there's some models in which we don't know if topological phases exist, and so we wanted to target a model for which it's much harder to understand whether that's the case or not. Okay, so it's basically this model is a model of bosons hopping on a lattice subject to some sort of interaction. So this is on the Kagome lattice, and the idea is that for a very large interaction V, this model is supposed to go to a phase that's called a topological spin liquid that has this log 2 quantity that becomes non-zero, and it's hard to, so far with other techniques, it's been hard to understand if that's the case. So we looked at it, and then what we found is that it's much more difficult and less clean than in the other model, in the toric code, but we were able to see that at least the calculations that we have suggest that this model actually plateaus around like this topological entanglement entropy plateaus around log 2. Okay, so it matches our expectation, and it matches more or less what people had thought of about this earlier, so that this point in which you get this log 2 behavior is around 8, which happens to be where our recurrent neural network sees indication of this quantity saturating around log 2. Okay, so that's kind of like abstract, but exciting. But there's a reason why we wanted to do this, right? Like, and the idea is that people conjecture and run simulations that there's a very interesting system based on atom arrays of Rydberg atoms on Kagome lattice, and they conjecture and then provide evidence that this model realizes such a topologically ordered phase. Okay, and the idea is that the physics of that problem is described by a Hamiltonian that looks a little bit like this. So it has a kinetic energy term, it has a potential energy, and then an interaction like within the Rydberg atoms that's long range. Okay, and this Hamiltonian has a very rich phase diagram. It has multiple phases: a paramagnet, which is basically kind of like a trivial state. It has a stagger phase and a nematic phase, and then there's a conjecture around here in the phase diagram as a function of delta and this Rydberg, and V, this term here, or the amplitude of this term here, that there's a conjecture that there's a spin liquid phase. So there was that came in 2021 in this proceeding of National Academy of Sciences paper, and they predict this topological phase. Okay, but then interestingly, there's another paper that studied the same system with a different technique, where they claim that instead they see a glass phase. So as in like in a similar amorphous phase of matter, similar to a real glass. Okay, and so we got interested. We thought this is an interesting example because the first paper uses or used tensor networks which are limited in some sense, right? Like in the sense that entanglement entropy is really strong and it performs really well in one dimension, but this is a two-dimensional system on the Kagome lattice. So we thought, okay, our architecture doesn't suffer from this issue of dimensionality because we can define, and people even in machine learning and computer vision had defined neural networks or recurrent neural networks in two dimensions. So we thought maybe we won't have like the same limitations as this models. And then so we bypassed whatever potential bias hopefully this first paper may have. And then the other paper, this PRL Physical Review Letters paper in 2023, used a technique called quantum Monte Carlo, which tends to break down in the presence of glassy phases or disordered phases. Okay, so then basically, okay, so both papers have limitations, or both techniques have limitations, and then the other thing is we think our architectures can bypass those two limitations. So in the first example I already said is because we are not limited to low dimensional systems. We can define this recurrent neural networks in any dimension. And then in the second case, so the recurrent neural networks can be sampled efficiently and exactly. So they don't have problems with critical slowing down or slowing down because of glassy dynamics and so on, which affects the techniques that they use in this regional 2023 paper, which uses Markov chains, which become very slow when you have a very rugged energy landscape. Okay, so then the idea was, okay, let's see if, of course, our approach would have its own limitations, but let's see if we can bypass this, and if we do, then that's great. Okay, and then we tried again a recurrent neural network defined in 2D, particularly targeting this geometry in particular, and then we asked the question, okay, can we target this regime where they see either a glass or a topological phase? Okay, so that was the hope, and that was recently published in Communications Physics as this this reference here, and but let me show you the results. Okay, so basically the idea is that we travel we traveled the following path. We went from this point to this point, which is where like this phase of matter, this exotic phases of matter are supposed to appear. Okay, so we target this like this kind of like this line that I'm trying to highlight here. Okay, so let me show you what happens or what our wave function predicts. Right, like so first we computed this topological entanglement entropy that if we had an exotic phase of matter should predict log2, which is this black line here. But and we're confident that our wave function is capable of capturing these phases of matter because we tried extensively on models where this is known to occur. So we're confident that our wave function can capture this log2, but instead what we found is that it has exactly zero topological entanglement. Okay, and then so we're able to conclude that with high accuracy that this wave function is not topologically ordered, at least within our calculation. Okay, and then we also computed the second order parameter, which is basically the computation that people had computing in this Physical Review Letters paper, and again they found the difference from zero, and we find zero throughout the whole line that we crossed. Okay, we see no evidence of the system developing any of the phases that they had predicted, which in our opinion, like based on our predictions, what we think is what's going on is that this is a very simple scenario, right? Like, so it's basically that instead of the system transitioning for very simple paramagnet, so this PM phase here, into a sophisticated exotic phase of matter, what happens is that there's nothing. That this whole line up until the points where we explore is basically the same phase as the paramagnet. So there's no evidence of the system transitioning to any different phase of matter, right? Like, so that's the conclusion, and that's what our neural net predicts. It's if you take Occam's razor, so basically Occam's razor is basically telling you choose the simplest explanation. The simplest explanation is that nothing happens, right? And that's what our wave functions, our recurrent neural networks predict, which are, I mean, they contradict these two papers, but we think this is just a very simple paramagnet. And if you want, like, as the last thing, basically it's telling you that there's neural networks and so on, and the wave functions are starting to become a useful tool to make predictions or to debunk them, if you want, from other techniques. So so we're really excited about the future of these ideas and so on. And yeah, with that, I'll conclude. So I think recurrent neural networks and other autoregressive models offer a very interesting platform to study quantum problems. They can be applied to many different systems, including problems in chemistry and material science, and strongly correlated systems and cold atoms, such as the ones that I just described, even for problems where there are no techniques. So I think this is opening really space for exploration and new physics and so on. And yes, I'm excited about the future this techniques hold. And yeah, with that, I conclude, and thank you all for your attention, for coming, and for the invitation to First Principles.